Welcome to Mission Control. I am your flight director, and today we are initiating a full-scale launch simulation for one of the most critical orbital pathways in the Cambridge Mathematics AS and A-level syllabus, 1.1 Quadratics. Specifically, we are locking our targeting telemetry onto solving quadratic equations and inequalities. If you are preparing for paper 9709, you already know this is your foundational propulsion system. It appears in practically every single examination series. But listen to me very carefully. Today, we are not just going to passively read textbook formulas. We are treating this syllabus like a critical flight launch protocol, and in this command center, there is zero margin for error. We are going to systematically deconstruct this topic by thinking exactly like an elite Cambridge examiner. Now, you are part of my flight crew today, alongside pilot Alex, our brilliant propulsion engineer who sometimes burns way too much energy by overloading the system with raw facts, and pilot Sam, our navigation specialist who steers incredibly fast but has a bad habit of completely ignoring structural boundary coordinates, what we call command words. We have a 15 to 20-minute launch window, so strap in, calibrate your monitors, and let's initiate the sequence.
Okay, let's bring up the launch roadmap on the central console. To get your trajectory perfectly aligned with examiner expectations, we will be clearing 4 distinct atmospheric layers today. Number 1, the core principles, where we establish the theoretical foundations and structural integrity of your math. Number 2, the procedural framework, which is the technical methodology and pre-flight checklist you must adopt. Number 3, the absolutely vital method mark strategy, which is essentially your fuel conservation protocol. And finally, number 4, top examiner warnings. We are going to look at real-world telemetry from past missions to keep you out of the most common gravitational traps. Let's get this bird off the ground.
Section 1 is Core Principles, the standard of excellence. We begin our calibration by establishing the strict academic benchmarks and conceptual frameworks that Cambridge demands. I am currently projecting a complex, multi-part Cambridge past paper question onto the central viewing monitor. Consider this your target orbit profile. We need to trace exactly how examiner expectations scale from standard recall data points, your basic factoring and expanding, all the way up to elite evaluation metrics. Understanding these scaling assessment objectives is exactly what separates an average student floating in low Earth orbit from a top-tier candidate who completely clears the atmospheric limits.
Look closely at this quote flashing on the main dashboard, pulled straight from the official assessment framework. Cambridge explicitly prioritizes analytical depth over superficial breadth. So what does that actually mean for you when you're staring down a complex quadratic inequality with the clock ticking? I'm looking at pilot Alex's terminal right now, and Alex, you are making a classic mistake. You are overloading the fuel logs with every single factoring trick and raw formula you've ever memorized. That is superficial breadth. You are going to burn out before you even reach altitude. The syllabus explicitly requires logical, structured reasoning. The examiners value deep, evidence-based analysis over mechanical processing. They want to see a high-propulsion evaluative launch pathway, not just a low-altitude descriptive trajectory. If the command word says hence or justify, and you just dump a formula without showing the logical connection to the previous part of the question, that is an immediate system failure alert. You have to prove you truly understand the mathematical machinery at work.
Now, what's really interesting about this slide is the core concept of transferability. Top-performing candidates don't just learn how to solve a standard, perfectly packaged quadratic equation. No, they build a connected, structural understanding that holds up even when faced with completely unfamiliar problem contexts. You might open your exam paper and get a question framed around a complex physical scenario, a projectile motion problem, or a financial profit-loss model that, when you strip away the outer hull, ultimately boils down to a core quadratic inequality. The fundamental principles must be so deeply ingrained in your navigation system that you can instantly recognize the underlying quadratic nature of the problem, no matter how strangely Cambridge has dressed it up. Your logic has to hold firm in any atmosphere.
Moving to Section 2, the procedural framework, the blueprint. Let's transition to the active phase of the flight and see how all this theoretical math builds into the rigorous procedural framework required for data interpretation and real-time problem solving under exam pressure.
This brilliantly illustrates the standardized sequence for systematic processing. Whenever you encounter a quadratics problem, you need to run through this exact blueprint like a pilot running a pre-flight checklist. Let's do this live. Step 1, identify the key elements. Sam, look at the coordinates. Are we dealing with an equation or an inequality? What are the coefficients? Step 2, apply relevant principles. Alex, you need to choose the right propulsion engine. Are we firing up the discriminant diagnostic, or are we initiating the completing the square thrusters? Step 3, execute your analysis with absolute crystal clarity in your working. No skipped steps. Step 4, verify your results. Do your roots actually make sense in the physical context of the problem?
And finally, step 5, present your answer in the appropriate format, such as exact set notation for inequalities. I'm telling you right now, skipping any of these steps leaves critical marks on the table and destabilizes your entire flight path.
Section 3. The method mark strategy, the execution. This is where the peer telemetry coordination debate really heats up. The absolute crucial point is how we execute this problem-solving loop in the actual exam environment to maximize our score. We are talking about the secondary booster strategy that can literally save your grade even on your absolute worst day.
Read this definition on the HUD, the method mark strategy. In Cambridge exams, marks are heavily awarded for demonstrating a logical process and systematic execution, completely independent of the final answer. Listen to me. By ensuring your working out is highly visible, perfectly clear, and logically sequenced, you secure these vital method marks. If your final thruster misfires and you accidentally drop a negative sign in the very last line of your calculation, yes, you will lose the accuracy mark. But your solid, visible methodology will have already banked you the vast majority of the points for that question. You secure the high-tier marking bands before your time fuel hits 0. This is exactly why showing your work isn't just a polite suggestion from your teacher, it is the absolute core of your survival strategy in this exam.
To successfully implement this strategy under extreme simulated clock pressure, you need to lock into this 3-step continuous loop: deconstruct, solve, and evaluate. Alex and Sam, I'm watching your screens. First, break the given information into logical steps. Deconstruct what the payload is really asking. Next, solve systematically. Alex, I see you writing, but ensure every single line of algebraic manipulation flows clearly and undeniably from the line above it. Don't skip steps in your head. Finally, evaluate. Sam, you're navigating way too fast. You rushed the final answer, but you didn't critically evaluate the results. Ask yourself, does a negative root make sense if we are calculating a physical length or a time value? No, that is a structural boundary violation. Checking for reasonableness is a high-level flight skill that examiners actively sweep for.
Launch trajectory hold all telemetry. Before we clear orbit and I show you how to deploy this top-band analytical framework, we need to optimize your educational flight deck. Take exactly 1 second right now to hit subscribe on the Ace the Exams channel at Ace the Exams and enable all notifications. Whether you are launching at IGCSE, O-levels, AS, or A-levels, you do not want to miss our weekly flight-tested exam hacks. Okay, system is optimized. Back to the simulation. Look at the text comparison on screen. Notice the massive difference between a purely descriptive approach and one that is analytical and evaluative. Warning, I'm seeing a structural data loss mid-equation on pilot Sam's screen. The evidence links are dropping and the mission is threatening termination. Sam is just describing the math, not evaluating it. I am overriding the console and deploying a structural power-up framework, the Peel structure. Point, evidence, evaluation, link. Let's rewrite Sam's response out loud right now. Point, state the condition for real roots. Evidence, apply b squared minus 4ac is greater than or equal to 0. Evaluation, calculate the critical values systematically. Link, definitively state the range of k that satisfies the context. You must justify your choice of method and make evidence-based conclusions. You are proving your mathematical fluency, not just your basic arithmetic skills.
Section 4. Top Examiner Warnings, the Pitfalls. We are now pivoting to real-world flight data pulled directly from Cambridge Principal Examiner reports. We are going to uncover exactly where previous candidates' logic failed so you don't steer your ship into the exact same asteroids. Hazard radar is officially activated.
I am now handing control over to you, the audience, for a live radar check challenge. Welcome to the Interactive Viewer Controls Arena. Challenge 1, the Visual Radar Sweep. I am putting a complex quadratic source data chart on your screen mentally right now. I'm starting a 60-second visual countdown. You need to extract the core trend. What's the biggest pitfall? Time's up. Did you spot it? Look at bullet point 1, using the wrong approach for the context. For example, burning 5 minutes using the quadratic formula when a simple graphical sketch would have immediately revealed the solution to a basic inequality. Now for challenge 2, identify the logic malfunction. Look at a flawed student response. Where did they drop the score? Right there at bullet 2, forgetting to check format and presentation. If the command asks for exact values and you provide a rounded decimal, your system fails. And finally, bullet 3, answers are not specific to the context given. You absolutely must ensure your final answers are distinctly tailored to the specific parameters of the question, rather than just providing a generic, robotic formula response that ignores the physical constraints of the problem space. The radar is picking up a major alert directly from the official examiner reports. Listen to this.
candidates consistently confuse key terminology. Before you dive into a massive block of algebra, particularly in extended modeling questions, you must always define your terms. If you decide to introduce a completely new variable, let's say k or m, to represent a constant in your quadratic setup, you have to state exactly what it is. If you don't declare it, the examiner's radar cannot track your logic. Clear communication is a highly tested mathematical skill. Defining your terms anchors your logical flight path for the examiner who is trying to read your telemetry.
Alex and Sam are confirming a successful full-mark launch sequence. I'm watching their propulsion meters absolutely peaked at a maximum A-star reading right now. Outstanding work, crew. As we reach the summit and complete this flight, I want to distill this entire session into 3 universal rules for you. First, the 3-step question scan. Always decode the command words and constraints. Second, fuel budget allocation. Manage your time and secure those method marks even if you're stuck. And third, the post-launch system review. Always evaluate your final routes against the physical context. So I leave you with this final, vital question. Are you building superficial breadth, just memorizing steps? Or are you mastering the systematic depth required to truly conquer 1.1 quadratics? Reflect on your current study habits. To ensure your next mission is a flawless success, subscribe to Ace the Exams at Ace the Exams, click that notification bell for our weekly grade masterclasses, and drop a comment below sharing exactly which Cambridge subject and level, IGCSE, O, AS, or A-level, you are preparing to conquer next. Flight Director, signing off.